Good morning, everyone. This morning we have Randy Levesque from University of Washington, who's here until the end of next week and has today's talk and a couple of talks tomorrow as well.
Thank you. So, what I'd like to do is just describe some of the methods that we use in my group and in the software package Clawpack that I've been working on developing for going on 20 years now. And in the last few years, there's been a lot of other groups that have started coordinating with us and working on various aspects of this as well. So I'll say a little bit about Clawpack as we go along. Clawpack stands for Conservation Laws Package. It was originally designed for solving nonlinear hyperbolic conservation laws, although we've applied it to other hyperbolic problems that aren't necessarily in conservation form, but it's basically aimed at hyperbolic systems of equations in 1, 2, and 3 space dimensions with adaptive mesh refinement and whatnot. So, but my goal today is mostly to talk about the underlying algorithms and the ideas that are used in this software and hopefully may be useful in other contexts as well. So the form of equations that we look at are always first-order hyperbolic systems of equations, or you could add in source terms or other terms on the right-hand side here instead of 0. Those can be incorporated as some sort of fractional step method, or at the very end, I'll talk a little bit about well-balanced methods for source terms that have to balance with the divergence of the flux term. But to start with, at least we'll look at a homogeneous equation, either a linear system of hyperbolic form, where Q is some vector with m components, perhaps, a vector of conserved quantities if it's a conservation law. A, in the linear case, A is just a constant or possibly spatially varying matrix, coefficient matrix. In the nonlinear case, this is generalized to the time derivative of the vector Q plus the x derivative of some flux function f of Q, which might be a nonlinear function from Rm to Rm. If we differentiate this f of Q, the x derivative of f of Q, we could rewrite this as a Jacobian matrix f prime of Q times dq dx, which is called the quasi-linear form because it's quite similar to the linear form, except this coefficient matrix f prime of Q would now be a function of Q in the nonlinear case. But at any rate, if this coefficient matrix, either A or f prime of Q, is diagonalizable and has real eigenvalues, then this system is called a hyperbolic system of equations. And these equations, of course, always arise when you have problems that model wave propagation or advection, transport, that sort of thing. And the eigenvalues of the coefficient matrix typically represent the wave speeds or transport speeds, characteristic speeds. The eigenvectors of the matrix represent sort of the relationship between the different components of Q that have to hold in a wave propagating with one of the particular wave speeds. So the eigenvalue, eigenvector decomposition of this coefficient matrix in the linear case, that tells you everything and you can write down explicit solutions. In the nonlinear case, it's a little more difficult to see how to use that. And so what we do is to use what's called the Riemann problem, which many of you may be familiar with, which is kind of a generalization to the nonlinear case of this idea of splitting into eigenvalues and eigenvectors. Of course, there are also second-order hyperbolic equations like the standard wave equation, but you can look at that as a first-order system of equations, or you can derive this from a first-order elasticity or compressible gas dynamics sort of equation. So we always look at things in this first-order form. And the methods that we use are finite volume methods, which are related to both finite difference and finite element methods, but somewhat different sort of philosophy. In a finite difference method, you would think of approximating the solution Q at discrete points by some Qi n, say, at point xi tn, replace the derivatives with finite differences and get an algebraic system to solve. That's fairly simple, but it assumes that things are smooth in order to be able to do that accurately. The idea of finite volume methods is that instead we look at Qin as representing an approximation to the cell average of the quantity. In 1D, it would just be the integral divided by the length of the grid cell. And then the methods are derived based on the integral form of the conservation law, which is often the more physically relevant form of the conservation law to begin with. So a conservation law typically arises from saying that the time derivative of the integral of this q, which we could view as a density function for mass or momentum or energy or whatever, the time derivative, the integral, the total mass within the grid cell, changes only due to the fluxes in or out of the cells at the edges. So if we don't have any source terms and things are not created or destroyed within the interval, then the only change in the integral is due to the fluxes at the boundaries. And if you take this and now you rearrange this, you write this as a spatial integral of df dx, then you can derive from this integral form, you can derive the differential form of the conservation law, but doing that requires smoothness, whereas this integral form requires less smoothness. And so if you base the numerical methods on this sort of integral form, then it's much easier to develop methods that work well for shock waves, for example, which is a standard characteristic of nonlinear hyperbolic problems, that you can develop shock waves in the solution, which are discontinuities in the solution that develop in finite time, even from smooth initial data. So the methods we look at have been developed specifically to deal with nonlinear problems where you have shock waves in the solution. And the basic method that everything that we look at is sort of based on is what's called Godunov's method, which was developed in the 50s, originally for gas dynamics, compressible gas dynamics problems. And the idea in one space dimension, if we look at the x-axis and then time going upwards, is that you view the solution at time tn as a piecewise constant function with cell averages given by qin at this time. And then as you evolve forward in time, if you start with piecewise constant initial data for a hyperbolic problem, what happens is that you simply get a set of waves that propagate away from the interfaces. So where you have a jump discontinuity in Q, that gives rise to a set of waves that propagate with finite speed in a hyperbolic problem. And in between these spans of waves, the solution remains constant until the waves arrive. And this problem, where we take our original conservation law and take initial data that's piecewise constant with a discontinuity at some point, is what's called the Riemann problem. And the software and the methods that we use are based on being able to solve this Riemann problem at the interface between each pair of grid points. And then I'll discuss in a minute how we extend that to more than one space dimension. But it's still based on looking at one-dimensional Riemann problems normal to the edge of each grid cell. And from each Riemann solution, we calculate a set of waves that propagate and the speeds at which they propagate, and then those go into a formula for the numerical method, basically. So if we look at a simple case, the shallow water equations, nonlinear system of two equations for mass and momentum. H is the depth of the fluid, U is horizontal velocity, depth averaged equation. If we take what's called the dam break problem, that's one special case of a Riemann problem where we have zero velocity everywhere, but we have a jump in the depth. And the color here is simply a passive tracer. I've really added another equation to this for the advection of a passive tracer, just so you can see how the water actually moves. If we start with this initial data and then we break the dam, initially, what happens is that we get, in this case, two waves propagating. The one propagating to the right is a shock wave or a hydraulic jump where there's a discontinuity in the depth and the velocity. The wave traveling to the left is a rarefaction wave or an expansion fan where the water is smoothly accelerated to the right through here. And if you look at the solution at different times, you see that it's a similarity solution. The solution looks exactly the same, it's just stretched out further. So if we look at this in the xt plane, from this initial discontinuity, we have the shock wave propagating to the right. We have a rarefaction fan propagating to the left, but the solution is constant along any ray. And there's also a contact discontinuity, which in this picture is where the red water and the blue water are in contact. If we have the third equation for the advection of that color variable, then it would have a jump discontinuity propagating at some intermediate speed. If we extended this to the Euler equations of compressible gas dynamics in one dimension, you get a very similar structure. If you looked at something like the pressure, you would have a shock wave and a rarefaction wave, but there would also be a contact discontinuity where the density could be discontinuous, but the pressure and velocity would be continuous. So this is sort of a special case of that. So that means that for this Riemann problem, for any given states, HL and UL on the left and HR and UR on the right, we can solve, it turns out, for what the Riemann solution is. And depending on these two states, you might get a shock wave and a rarefaction wave as here, or you might get two shock waves or two rarefaction waves. But it always has the same sort of structure. It's a system of two equations, so we get two waves, or if we add the tracer, we get a third wave responding to that. And in this case, you can actually solve the nonlinear Riemann problem for any states, at least, well, it reduces to a scalar nonlinear equation that you have to solve by some Newton's method or something like that, but modulo that, you can find the exact solution of the Riemann problem. But since we're doing this at the interface between every pair of grid cells every time step, we typically don't solve the full nonlinear Riemann problem. Instead, we do some sort of linearization. So if these two states are close to each other, which they will be most places in a smooth solution, then you can replace this nonlinear problem with some linear problem. And so we would replace the nonlinear problem with a linear problem where the coefficient matrix is based on the states to the left and the right. And there are various ways to do that. Phil Rowe developed an idea in the late 70s, I guess, called the Rowe solver that gives a nice solution to that because it also has the property that not only does it sort of approximate the solution well when things are smooth, but if you have a solution that consists of a strong shock wave, it also captures the shock wave properly. So that's just a particular way of doing the averaging of the Jacobian from the two sides that then gives you a linear problem that's easy to solve just by finding the eigenvalues and eigenvectors. And so in general, in the methods I'll be talking about, even though we're looking at nonlinear problems often where you have rarefaction waves, we'll think of the solution as simply consisting of discontinuities. This linear problem has a similar structure, but each wave is a jump discontinuity propagating at a speed that's given by an eigenvalue of the matrix, and the jump across each wave is the corresponding eigenvector, proportional to the eigenvector of the matrix. Okay, so if we have a way to solve the Riemann problem for whatever problem we're looking at, then we can use that to develop a numerical method. So as I said, Godunov's method you can think of in various ways, but the first step is to solve the Riemann problems at each point. And then after doing that, one way to think of it is that you simply take this structure that is the exact solution with this piecewise constant initial data, and then average that solution over each grid cell to get the new cell average at the end of the time step, and that's your used to then define the piecewise constant function at the beginning of the next time step. So conceptually, that's what Godunov's method is. But it's a little hard to implement that way to figure out sort of what is the average over a grid cell. So there are ways to rewrite that. One way that's often done is to write it in flux differencing form. It turns out that the relation between the new cell average and the old cell average can be expressed just in terms of the difference between the flux at the right edge and the left edge. And because these Riemann solutions are similarity solutions, the solution along these dashed lines here is constant in time, so you can work out explicit formulas for the flux based on the Riemann solution. So for conservation laws, things are often written in this flux differencing form. We want to also apply these methods to problems that might not be in conservation form, but are still hyperbolic, like if you have a variable coefficient a of x times dq dx. And so we express them in a somewhat different form. We use this, what we call the wave-propagation form, which is to update the cell average by each of the waves that comes out of the Riemann problem and look at the contribution that each wave makes to the cell average individually, and then sum them all up. And so in notation, we write this as the cell average is updated by some contribution coming from the left edge, I minus a half, which I'll write as a plus times delta q, which sort of represents the right-going set of waves coming from the left edge of the cell, and then there's a left-going set of waves coming from the right edge of the cell. The first way that I described you could also think of as reconstructing from your cell averages a piecewise constant function, evolving the hyperbolic equations exactly with that initial data, and then averaging over the grid cells. Again, rather than actually computing this average, instead we look at the contribution that each wave makes to the cell average. So if we were looking at a scalar problem, scalar advection equation is the simplest hyperbolic equation. Then from the cell averages, which are the dots here, we would reconstruct a piecewise constant function, and then we would solve the advection equation, which if it were just a constant coefficient advection equation, would simply translate the solution a little bit to the right, say, if the velocity were positive, and then we would average the solution on each of these grid cells to get the new cell averages. And if you look at what happens in a single grid cell, the cell average is updated by the jump that's moving in from the edge, which we can view as the wave here, multiplied by the distance it's going, which is the velocity u times delta t. So it's that velocity times the jump or the wave strength divided by the cell average in order to give an update to the cell average, or rather divided by the cell length in order to give the appropriate update to the cell average. So if you plug this in, then we're updating the cell average by this quantity, and this just gives the first order upwind method, which you can easily drive as a finite difference method, but this is sort of the finite volume interpretation of the upwind method, this special case of Godunov's method. How do you extend this to a system of equations? Well, if we have a linear system or a nonlinear system, we would typically approximate, as I said, at each interface by some linear problem. Then the jump between qi and qi minus 1 is a vector with m components. We can write that vector as a linear combination of the eigenvectors. So the rp here are the eigenvectors of A, p going from 1 to m. The alphas are scalar coefficients. So we can write this as a linear combination of the eigenvectors. And it's this combination, alpha times rp, that we call the pth wave. So each of these waves you should view as, or think of as a vector, which is proportional to an eigenvector of A. And each of these waves represents the jump in Q across the wave, and the cell average, therefore, is updated by a contribution from all of the waves that enter this grid cell. So in this case, there's two waves entering from the left, the 2-wave and the 3-wave, and one wave entering from the left, or from the right, rather, one negative eigenvalue and two positive eigenvalues in this case. And so the update to the cell average would depend on the strength of the 2-wave and the 3-wave multiplied by the speed they're going at, lambda 2 times lambda and lambda 3. And from the left, there's one wave traveling at speed lambda 1, which would be negative here. And so this is the update corresponding to Godunov's method for a system of equations, and it's a direct generalization of the upwind method to working in characteristic variables, basically. We could also derive this by taking this equation and diagonalizing it, and then applying the upwind method to each of the three characteristic variables separately. But the nice thing about looking at it this way is it extends directly to nonlinear problems. If we don't have just a constant coefficient linear problem, but a nonlinear problem like shallow water or Euler equations, we can still, at each interface, we can define these waves by solving, either exactly solving the Riemann problem or using some approximate Riemann solver like the Rho solver. We get a set of waves propagating at a set of speeds, and we plug them into this formula, and that's Godunov's method. So the general formula, if we had a system of m equations, you could write this way. From the left edge, I minus a half, we have all the waves propagating in for which the speed is positive, so this s plus is 0 if s is negative. And similarly, from the right edge, we have contributions from all the waves that are propagating to the left. Okay, so this is the basis for the software we use. Now, it's only first order accurate because it's generalization of the upwind method, and I'll talk in a moment about how to make this second order accurate and improve the accuracy. But this is the sort of the basic idea of these wave propagation algorithms as we implement them. And so say just a little bit about ClawPack, which is the software that we've been developing that implements these methods and extends this also to 2D and 3D. This is all open source code. The bulk of it is written in Fortran, although we use Python now for the user interface and the graphics part of it. It has adaptive mesh refinement. I've been working with Marcia Berger at the Cron Institute pretty much from the beginning of this project to incorporate the adaptive mesh refinement algorithms that she's developed into ClawPack. It's a patch-based algorithm where you refine on rectangular patches. So I should say this code is always based on rectangular, or at least logically rectangular grids, even in 2D and 3D. I'll say a little bit more about some applications of that at the end. There's a number of variants recently that have been developed. GeoClaw, which we've been working on for close to 10 years now, is a specific version of ClawPack for geophysical flows over topography. In particular, tsunami modeling is something we've worked on a lot recently, but also storm surge, debris flows, avalanches, things like that can be handled as depth-averaged equations over topography. PyClaw is a version that uses Python more extensively and is also coupled with PETSI for applying on massively parallel computers using the the MPI rather that's built into PETSI. ShortClaw is a version that former student David Ketchison at KAUST has developed for doing higher order methods using Wino approximations, so higher than second order. MiniClaw is a version that's being developed for GPUs and other architectures. ForestClaw is something that Donna is working on using P-Forest as another way of implementing adaptive refinement on parallel machines. There's a number of activities. You can find links to most of these things at the main webpage. But the basic idea of the structure of the code is that the user specifies the problem that's being solved by providing a Riemann solver. And we have Riemann solvers for a lot of standard problems like Euler equations, shallow water, acoustics, elasticity, and so on. But if you had an exotic problem, you would have to develop a Riemann solver that basically splits any jump in the solution between two grid cells into waves and speeds. And then you also have to specify boundary conditions. That's done by filling in ghost cells around the edge so that Riemann problems can be solved also into the ghost cells, and basically the same algorithm can then be applied a little beyond the boundary so that you can update everything in your actual region of interest. For standard boundary conditions like outflow boundary conditions, periodic boundary conditions, solid wall boundary conditions for Euler or shallow water, those are incorporated in the package, or you can provide more exotic boundary conditions specifically. And then, of course, initial conditions, source terms, if there's a non-zero right-hand side, can also be added in. So the Riemann solver, again, is kind of the fundamental piece of the code. And again, it just takes as input the value of Q in each cell, and as output produces a set of waves and corresponding speeds. And these fluctuations is the term we use for this sort of combination, the sum of SP times WP over all the left-going waves and over all the right-going waves. So those are also vectors in RM. And the number of waves that come out is typically equal to the number of equations in the system, but it doesn't necessarily have to be. So, for example, there's the HLL, Harton-Laxton-Lear approximate Riemann solver, where you always just use two waves to approximate the Riemann solution with a constant state in between. That could also be incorporated into this frame. So how do we get to second order accuracy? Because first order upwind method is really not accurate enough for most applications. So there are various ways to look at how the extension to second order goes. If we just had a scalar equation, then a simple way to think about it, and I'll present this first and then show how it extends pretty naturally to systems, would be to generalize this reconstruct, evolve, average sort of algorithm to replace the first step where we just took a piecewise constant function and instead generate a piecewise linear function from the given cell averages with some slope sigma in chosen in some way that this gives a reasonable representation of the function, which I'll talk about in a moment. And then conceptually, at least, you could think of solving the hyperbolic equations exactly with this piecewise linear initial condition and then averaging the result over the grid cells, and that would give you a second order accurate method if you choose these slopes appropriately. Of course, that requires solving the hyperbolic equations with piecewise linear initial conditions, which for a general system is not nearly as easy as for piecewise constant. So instead, we'll rewrite this in terms of using the waves and speeds that come out of the Riemann solution. But conceptually, at least, you can think of it as taking the cell averages, reconstructing some sort of piecewise linear function. If it were just the advection equation, then that would simply shift at speed u, and then average this piecewise linear function over the grid cells. The way I've chosen the slopes here is to look at each grid cell average and look at the average to the right and take that slope. So here I've got a slope between these 2 points in this cell. In this cell, it's the slope between these 2 points. In this cell, I've used these 2 points, and so on. It turns out if you do that, you plug it into this formula for the scalar advection equation, what you get is the Lax-Wendroff method, which is a standard second order accurate method. However, it has problems, as you're probably aware. Lax-Wendroff tends to be dispersive. If you have a discontinuity, a shock wave, then it introduces oscillations. And you can sort of see why that is, because when you're sort of always choosing the slope based on the point to the right, you can get undershoots in the piecewise constant function relative to the actual data that you started with. If you have a piecewise constant function, then there's going to be one cell where you have a non-zero slope that's going to give you an overshoot or an undershoot, and that gives rise to dispersive ripples. So rather than always choosing the slope by looking at the cell to the right or by looking to the cell to the left, which would give the beam warming method or some other fixed formula, instead what's used is some sort of nonlinear way of choosing the slopes based on how the data is behaving. So one standard limiter, as it's called, that's often used is the min-mod limiter, which in the context of reconstructing a piecewise linear function just says that in each grid cell, we look at the slope to the left and the slope to the right, and we take the one that has the minimum modulus, the one that is smaller in absolute value. And if the slope to the left and the slope to the right have opposite signs, as at this point, then we set the slope to 0. So that has the advantage that we get a reconstruction that doesn't introduce any undershoots or overshoots and gives non-oscillatory solutions if you start with a discontinuity, say, in your data. So this min-mod is one limiter that's been developed. The way it's being used here is as a slope limiter. There are other variants of these methods where people use flux limiters. You use a flux differencing form, but apply some limiter to the flux based on how the solution is behaving. There was a lot of development of these flux limiter methods in the 70s and 80s. It's fairly well understood what good choices of these limiters are for getting good accuracy without introducing oscillations. The way we use it in these wave propagation algorithms is to use the same sort of limiters, but view them slightly differently, view them as wave limiters, essentially. So we've got this wave, say in the scalar advection equation, the wave is simply the entire jump. Otherwise, this will generalize in a moment to a system where we split the jump into more than one wave. But if we just have a single jump, then the upwind method, again, we simply update the cell average by the wave times the fraction of the cell it moves through, basically. The Lax-Wendroff method, you can rewrite as being this upwind method plus a correction term that you can look at as being the difference in some flux F tilde between the right edge and the left edge of the cell, where this F tilde flux is defined in terms of the wave and the speed u in this case. And it's basically just adding in the next term in a Taylor series expansion for the cell average in terms of the original one plus delta t times the time derivative plus delta t squared times the second derivative in time. When you put this term in here and rearrange, you just get the standard Lax-Wendroff method. To turn it into a high resolution method with these limiters, we do exactly the same thing, except we replace the wave by some limited version of the wave. So for each wave, we determine some limiter phi that's depending on how the data is behaving around this point, and modify the amplitude of the wave by this scalar phi. So in the case of the scalar advection equation, if we have flow to the right, for example, if u is positive, then this limiter would be based on the magnitude of this wave, but then also look at the wave coming into the cell on the left, the one in the upwind side, and see how those two waves compare to each other in amplitude. And if they're comparable, then we're in a smooth region of the flow, and we should use this full wave to get a second order accurate method. But if they're very different, then we want to apply a limiter so that we don't introduce non-physical oscillations. So I won't go into the details, but that's kind of the basic idea. And then this can be extended to a general system of equations. So this is the sort of Godunov upwind method here. If we have a system of equations, we have the waves coming in from the right edge and the left edge. But now we add in this correction term, which looks the same as before, but now it's a sum over all of the waves. We have the corresponding wave with some limiter applied to it, and then we have the speeds coming into these formulas. So if this were a linear system and we didn't apply any limiter, then this would just be a sort of complicated way of writing the Lax-Weintraub method. You can see that it all collapses into the Lax-Weintraub. But once you introduce these limiters, then it works. It still gives second order accuracy where things are smooth, but it avoids oscillations and it avoids numerical dispersion to a large extent. And so the limiter is applied by comparing each wave to the corresponding wave in the Riemann problem, one cell upwind, either to the left or to the right. Okay, so extending to 2D. So if we have a conservation law in 2 dimensions, again, the integral form of the conservation law is that the time derivative of the integral over the cell is given by integrals of the fluxes around the boundaries. And you can, from this integral form, you can derive this differential equation, assuming everything is smooth. But again, the numerical methods are really based more on this form. And so if we replace this integral of q by delta x times delta y times some cell average, and we replace each of these integrals of f by some numerical flux terms, then we get this sort of finite volume form. You divide by delta x and delta y, then you get this form here where the cell average is updated by a difference of fluxes in the x direction and a difference of fluxes in the y direction. So again, there's been a lot of methods that have been developed sort of in this flux differencing form, but instead what we use is this fluctuation form that extends also to non-conservative hyperbolic systems where we look at the right-going waves from the left edge, the left-going waves from the right edge, but then we also look at the upward-going waves from the bottom and the downward-going waves from the top of the cell, and then we also add in correction terms that give us second-order accuracy with the limiters added on. So if we just look at the advection equation in 2 dimensions, say we have flow at this angle here given by these arrows, then in the simplest case, if we just looked at sort of Godnoff's method, what's sometimes called donor cell upwind, we would calculate what's going on by simply solving one-dimensional Riemann problems at the left edge and the bottom edge. At the left edge, we would have a Riemann problem involving the velocity u, and we'd get some wave moving into the right. At the bottom edge, we'd have a velocity v, and we'd have a wave moving upwards. And those two waves would contribute to the cell average. Because these waves sort of overlap, it turns out this method is only stable if this sum of the two one-dimensional Courant numbers is less than or equal to 1. Otherwise, you get an instability developing. It's also not very accurate because we're really not doing a very good job of approximating the advection in the proper direction. So you can modify this to get a better first-order accurate method by introducing advection in the appropriate direction. This is what's sometimes called the corner transport upwind method. And you can view it in the wave propagation form. You can view it as taking the jump between these two cells and looking at that wave as propagating not simply to the right, but actually upwards as well, because there's a vertical velocity v that's non-zero. And whatever jump you have down here is propagating to the right as well as upwards. And similarly at this edge down here, we have a wave that's propagating to the right and upwards. So if you look at this cell here, for example, this cell is being updated now by both of these waves, the one coming in from the left and the one coming in from below. But this cell, the same cell, is also being updated by this wave that's coming from the cell interface to the left here, and also by this one. So there's actually now 4 waves that update this cell average. And for a constant coefficient advection problem, you can see that another way to interpret that is sort of in the Lagrangian form, that we take this grid cell and we trace back in the characteristic direction, the advection direction, and we construct the grid cell that overlaps these 4 cells, and we take the appropriate weighted average of those 4 grid cells. It turns out doing that gives you exactly the same thing as updating the cell average by these 4 waves. But looking at it this way extends much more easily to systems of equations than trying to trace back characteristics and integrate over this rectangular region at the beginning of the time step. So by introducing this corner transport, we're in essence introducing terms that involve the cross-derivative terms, the xy derivative terms. It's still only first-order accurate because we haven't put in the qxx or qyy terms, but it's more accurate than the donor cell method, and it's more stable. It's now stable as long as the maximum of the one-dimensional prompt numbers is less than or equal to 1. So this modification that we're making by going from just the donor cell to the corner transport is that we've got a little triangular area here that we can view as having been shifted. This triangular portion of this wave, the jump across the wave times that area is being added to this cell up above instead of to this one. So we can view that as an additional flux at the interface between these two cells. So this little triangular area, if we do the first order update, then we have to transfer that amount from this cell up to the one above. And similarly, this little triangular area here is the amount we would transfer from this cell to the one over here. So if we look at this area up here, we can easily calculate that area. It's 1/2 base times height. And so that gives us an expression for the flux at this top boundary due to the transfer of that triangular portion from one cell up above. And you can see it involves u times v times the jump in q in the x direction here. But that's the flux at this top boundary. We do a similar thing here, and then both of those come into updating this point. And so in the end, what we get is like a y derivative when we difference this g tilde in the y direction of this x derivative times uv with a factor of 1/2, which is looking a lot like the term that we need in the Taylor series, which is shown on the next slide, I think, but it's basically approximating this cross-derivative term that comes into our second-order Taylor series expansion. Yeah, so in CLAWPAC, the way that this is handled is to have the user provide a normal Riemann solver, which takes, say, the jump in Q in the x direction between one cell and its neighbor, and splits it up into the fluctuation going to the right and the left by solving just the one-dimensional problem normal to the interface. In the x direction, that would just be qt plus a qx equals 0. So we can view that as sort of splitting up the matrix A into matrices A minus and A plus that have only the non-positive eigenvalues or only the non-negative eigenvalues in the eigenvalue matrix. In fact, these, what I call script A plus delta Q, the notation we use for general nonlinear problems, but in the linear case, it's really just one of these matrices multiplied by the jump in Q, gives you the contribution of all the left-going or right-going waves. And in CLAWPAC, you can specify dimensional splitting, where you solve in one dimension, update things, and then solve in the other direction. But the preferred way to do it is to use this more multidimensional approach, where we also include these corner transport terms. And so that's specified by a second Riemann solver that takes one of these vectors, these A plus delta Q and A minus delta Q are vectors representing the net contribution of waves going to the left or the right, and take that vector and split it up into eigenvectors of the coefficient matrix in the other direction. So in the one-dimensional case, A was just U and B was just V, but in the multidimensional case, A and B are both matrices, and we do a splitting, an eigenvector splitting in order to solve this normal Riemann problem, but then we take each of the resulting vectors and split them up into eigenvectors in the orthogonal direction. And again, this is really representing or building up another term in this Taylor series expansion. So if we had just a linear hyperbolic problem, if we expand in the Taylor series, first few terms, we replace qt by minus aqx plus bqy. That's what the first order upwind method is approximating. And then the second term, if you differentiate this equation, you find that qtt is equal to what's in the square brackets here. And we now replace these derivatives by approximations based on our cell average. And if you look at the terms that just involve A, the A delta t aqx, a half delta t squared a squared qxx, those terms are handled, or this term is handled by adding in a correction term based on putting in slopes with limiters in the x direction. Similarly, this term is based on adding slopes and wave limiters, second order correction terms in the y direction. And these cross derivative terms come from this sort of corner transport with the generalization of it. And if we take one of these matrices, say B times A, and rewrite it as a sum of B plus and B minus, where again, this has only the positive eigenvalues, this has only the negative eigenvalues, times A plus plus A minus, this product is really the product of 4 terms. And so this term, this BA, dq, dx, dy, is approximated not by just a standard approximation that's based on 4 cell values that's independent of the data. Instead, it's split up really into 4 terms that are based on how the data is behaving and what the characteristic structure of the system is. So one way to view this is if we are looking, say, at the Riemann problem here, we would first solve in the x direction, get the right going and the left going fluctuations, but then we would take this whole vector and we would split that up into eigenvectors of B, and that would result in an upgoing part and a downgoing part, so that this right-going wave is really viewed as a combination of these two, and similarly the left-going wave would be split into these two, and then each one of these triangular areas here would be used to update neighboring cells, or actually to define sort of a correction flux at this interface, a transfer of some of the mass of this A plus delta Q from this cell into the cell above. So you can build up sort of the updating formulas again by simply solving each of these Riemann problems, then solving the transverse Riemann problem, and then updating cell averages by the appropriate terms. And it looks a little complicated, but these areas, these are always triangles here, and so it's very easy to calculate what the correction terms are. And it can be applied on non-rectangular grids as well. Again, we typically use logically rectangular grids. You could do the same sort of idea, though, on triangles even, but on a sort of logically rectangular quadrilateral grid, it would be the same idea. You'd solve the Riemann problem in the normal direction. That would give you waves moving to the right and left. And then you would look at the other interfaces here and solve a Riemann problem, in essence, normal to each of those faces, but with data given by the right-going or left-going fluctuations from here. And that would give some transfer of those waves into the neighboring cells. And again, the area that you have to calculate here is always a triangle. So it's even on a general quadrilateral grid, it's easy to generalize these updating formulas. And we've also found that these methods work well even if you have very highly distorted grids. So you don't have to have a smooth grid in order for these methods to work quite well. So one thing that we've looked at is work with Donna Calhoun and Christiana Helzel and Marcia Berger on the adaptive side. We've looked at some grids on the sphere that are logically rectangular, but that are sort of folded over to cover the sphere. And we have some cells that are highly distorted here along the equator, and yet we get still second-order accuracy, particularly with these methods. So this is sort of how these grids are formed. I think Donna talked about this a bit at the PDs on the sphere meeting. And so I won't say too much about it, but basically you can think of taking a rectangular grid. I've colored in a couple of lines here just to see what happens to them as you create this grid on the sphere, but basically you fold it in half and match up the edges, and you get this sort of mapping onto the sphere. So the corners on the original grid get deformed into these nearly triangular cells, 4 of them on the equator. But it gives you a way of mapping a rectangular grid onto the sphere in such a way that it turns out the cell areas are nearly uniform over the sphere, so you don't have any small cell problems as you would have at poles, and it's a nice single rectangular grid. So it's an alternative perhaps to the cube sphere sort of idea that also gives you a way of mapping rectangular grids to the sphere. So we were interested in this. Well, I won't say too much about this, I'm running out of time, but I'm happy to talk to people more about this. We were looking at solving shallow water equations and keeping the 3 components of momentum in x, y, z in order to represent the flow field on the sphere, so you get this sort of system of equations. And then one thing that we were looking at is how do we apply adaptive mesh refinement. This was a motivation for trying to map a rectangle onto the sphere. We have this code that applies adaptive refinement on rectangular regions. By using this sort of mapping, we can apply adaptive refinement on the sphere by refining in computational space on rectangular patches. So this was a test problem where we looked at a sort of a radially symmetric type problem where we had a hump of water in the shallow water equations at around for the refinement patches here. There was also some variation in the bottom topography that was also symmetric about the sphere, sort of a ridge at minus pi/6 latitude. And this wave, as it moved southward, the adaptive mesh refinement followed that. I'll just show a couple of results. So this is as a function of latitude. It should be sort of one-dimensional, so you can calculate the one-dimensional solution on a very fine grid, the appropriate problem, and use that as a reference solution. So this is at time t=0. At a later time, it's propagated into the southern hemisphere here. 0 would be the equator. But because of this ridge, there's also some reflected energy here, and the solution should look like this. This is on a very coarse 100 by 50 grid, and this is with the adaptive mesh refinement by a factor of 4 in each direction. And the refinement region is sort of in between the black lines here in latitude. So it's a much better solution with refinement. We looked at it, the larger amplitude wave, where you actually get a shock wave developing as it propagates. And we've also looked at other problems. I'm sure know more than I do about the Rossby-Horowitz test problem, but this was just looking at the order of accuracy that we get after a certain number of days when we solve on grids. In this case, it was uniform grids, but refining by factors of 2. And we get not exactly second-order accuracy, but close to second-order accuracy, even though we have these very skewed grids near the corners on the wave. So finally, let me just say a little bit about the adaptive refinement. So as I said, this is all based on refining on rectangular patches. So we use the second approach listed here. And Marcia Berger has been heavily involved in the development of our code from the beginning. So we flag the points that need refinement on a level, and then those get clustered into rectangular patches. And every few time steps, we regrid. And then you can have several nested levels of grids. There's a number of questions that come up when you do adaptive mesh refinement. How to maintain conservation at the grid interfaces. Do we have accuracy at the interfaces? We want to avoid spurious reflections, for example. What sort of refinement strategy to use? Again, I'll be happy to talk more with people about these things later on. But let me just show one example. This is, as I mentioned, we've been doing a lot of work on tsunami modeling recently with the GeoQual version of the code. So for tsunami modeling, even though it's a two-dimensional shallow water equation problem, you really have to use adaptive refinement in order to resolve the sort of features that we want to look at in a reasonable amount of time. So here we were looking at the large tsunami off the coast of Japan, the Tohoku event from last March. And the grid that you see here is a coarse grid over the Pacific Ocean. Hawaii is where these dots are here. This is a zoom on Hawaii that at the moment looks pretty boring, but as we add more refinement, you'll see that come into focus. So we have one very coarse grid here where the grid spacing is 2 degrees, which is about 220 kilometers on the side. We use ultimately 6 levels of refinement to zoom in to Hilo Harbor with a resolution of a 1/3 arcsecond, which is about 10 meters on the side. So we've got a huge refinement between the coarsest and finest level. These are the ratios we go down by at each level, and going from level 5 to level 6, for example, is a factor of 45 refinement. So initially, we start with only 3 levels of refinement, this coarse one, and then there's a box here where I didn't draw the grid lines, where it's refined by a factor of 3, and then another box here where it's refined by an additional factor of 4. And we've specified here, since we're interested in Hawaii, we've specified what part of the domain is allowed to be refined. We don't really care about this wave that's moving northward here, so it's not as well refined. But you can see that we do capture sort of the waves even at the interfaces between the grid cells fairly well. At a later time, this is 5 hours after the event, although it only took so far 4 minutes of CPU time on the laptop. As we start zooming in and adding more levels of refinement, you'll see the CPU time go up quite a bit, but so far it's only a few minutes. As we approach Hawaii, we start to add additional levels of refinement here, and as it comes in closer, we eventually add in the 6th level of refinement near Hilo Harbor so that we can actually resolve the seawall, and these were 3 gauges where there was some actual observational data that we could compare against. Another thing I guess to mention is, well, again, here you can see that the waves behave pretty well at the interfaces between the different grid resolutions, and in general we find we don't have very much problem with even very large refinement ratios from one grid to another. Also, at the outflow boundary here where the waves are leaving the domain, what we do is simply extrapolation from the grid cells adjacent to the boundary into the ghost cells. And then when you solve the Riemann problem between a cell and the adjacent ghost cell, if they have the same value in them, then there's no waves, or there's 0 strength waves in that Riemann solution. And in particular, there's no incoming waves. And that's not a perfect non-reflecting boundary condition, but it does quite well. And we found that it's quite adequate for many problems. Okay. Finally, let me just briefly mention that another thing we've looked at a lot is this well-balancing issue. When we have shallow water equations over bathymetry, we have a right-hand side source terms in the momentum equations that depend on the gradient of the bathymetry. And so one issue is that we have, if you just have an ocean at rest, but you have rapidly varying bathymetry, these terms are very large, and also the gradient of the hydrostatic pressure, 1/2 GH squared here, is also large, and those terms should exactly cancel out in order to maintain the ocean at rest. And what we're looking at in tsunami modeling is a very small perturbation of an ocean at rest where there's often quite a bit of variation in bathymetry. So we have a sort of a quasi-steady problem where we have a lot of, or basically balance between the derivative of the flux and the source term, and the perturbation, the solution that we're looking at, is very small compared to those terms. So this application, we have shallow water equations over bathymetry, but similar things arise if you're looking at a stationary atmosphere where there should be a pressure gradient that balances gravity, and then you want to look at small amplitude waves relative to that. So just briefly, if you try to do a fractional step method where you alternate between the homogeneous problem and the source terms, that works great for some source terms. It works terribly here. You would, for the tsunami problem, you would end up generating waves that are hundreds of meters in amplitude on top of a flat ocean just by doing this sort of splitting. So instead, we have to incorporate the source terms into the Riemann problem, essentially, so that we take care of this balance between the flux term and the source term as we go along. This is just an illustration of the problem. This is a transect across the Pacific from another tsunami that went off the coast of Chile in 2010. This is what the bottom bathymetry looks like on that cross-section as a piecewise constant function. This is going down to 6,000 meters here in this trench. And from one grid cell to the next, there's often a jump of several hundred meters. But if you zoom in on the surface at the resolution of 20 centimeters here, you can see the tsunami wave. So we're trying to resolve something that's 20 centimeters in amplitude on top of something that's varying on the order of thousands of meters. And you really have to use this well-balanced method, or else you'll get huge inaccuracies in the solution. So the basic approach is to, as I said, incorporate this source term into the Riemann solution. And we do that by basically looking at the flux difference, adding in a correction term based on this source term, and then splitting up that vector as a linear combination of waves. So there's a variant of the wave propagation algorithm we call the F-wave algorithm, where we split up a flux difference rather than just the difference in Q's, and then you can incorporate the source term directly into that. And the advantage is that if things should be in steady state, then this flux difference divided by delta x should exactly balance the source term, in which case the left-hand side here would be the zero vector, and then you're splitting up the zero vector into waves, you get zero strength waves, and it doesn't change. Or if you're very close to steady state, the waves that you're working with and that you're applying limiters to for the second order correction terms are really the waves that represent the deviation from steady state, exactly what you want to capture. So, sorry, I think I've run over a bit. I'll stop here. If you're interested in hearing more, I'll be around for the next couple of weeks. Be happy to talk with you. A few references. There's a number of papers that you can find from the Quapac webpage and the GeoClaw webpage, which you'll find from there. And also, in many cases, the code that goes along with papers we've tried to archive there. I have a book by Cambridge University Press on finite volume methods that describes all of these algorithms in a lot more detail. A couple of papers relevant to what I was talking about here. Thank you.
Any questions?
Okay, so, the results for the Rossby-Horwitz wave showed good convergence, which made me wonder about the geostrophic balance between Coriolis and pressure gradient. But perhaps you answered that. Do you use the same sort of well-balanced, you bring the source terms over into the Riemann solver?
Yes, I believe we did for the Coriolis term there, yeah. I should check on that because I don't remember exactly how that was handled, but I believe that it was also incorporated.
Another question on...
Very general question. What makes the wave propagation viewpoint favorable over other viewpoints?
So I guess what I like about it is that it's a very general sort of framework where you can, once you have this sort of framework based on splitting up into waves and then applying limiters, it applies equally well to Euler equations, shallow order equations, elasticity. And it extends, because it's not in this sort of flux differencing form, it extends to non-conservative problems, which I didn't say too much about, but if you had, for example, elasticity in the Earth where you have varying material properties, then you can write that as a hyperbolic linear system if you're just looking at linear elasticity, but the coefficients would vary from one grid cell to the next based on the material properties. And if you have, say, two adjacent grid cells that have different material properties, you can still solve a Riemann problem in which the waves going into one side travel at the wave speeds appropriate for that material, and the eigenvectors you use are the corresponding eigenvectors for that material, and the waves going in the other direction, you use a different set of eigenvalues and eigenvectors relevant for that material. And so you can take an arbitrary jump and still split it up as a linear combination of those eigenvectors. And so you can handle sort of variable coefficient problems in exactly the same framework by looking at it sort of as how do you take these waves and apply limiters to them and use them to update cell averages rather than trying to define interface fluxes. So the Sharpclaw package that I mentioned that David Ketchison has developed for Wino methods, he's taken the same sort of approach. Wino methods were originally developed for conservation laws in terms of fluxes, so he extended that to handle also non-conservative problems so that you can do higher order approximations, spatially varying elasticity.
Any final questions?
Is there a hard-coded assumption of collocation here, or can the control volumes that you're integrating over be different for different variables?
For what we're doing, we're always using the same volume for all variables. So we have, our basic quantity that we're storing is the cell average over some fixed set of grid cells.
I mean, I guess you know why that's a controversial thing to do in at least some circumstances, right?
So there are cases, so there are situations, for example, where you have, say, variable coefficient advection, where you might want the advection velocities at the edges, I guess. And so when we look at variable coefficient velocity, if you're given the velocity field anyway, then we do actually look at evaluating the velocities at the cell edges, or some average of the normal velocity across each cell edge would be what we would really be using in our Riemann solver. So the Riemann solver at a particular cell edge would depend on the state variables on the two sides, but the velocity at the edge would define the velocity at which that propagates into one cell or the other. But if you're looking at something where you have, you're also trying to evolve the velocities, we have looked a little bit at incompressible flow, where we've kept track of velocities in the cell centers, but then we, imposing the divergence-free condition, we interpolate to edge values and apply the divergence-free property, or do the projection in terms of the edge values, and then use those edge values in terms of solving the Riemann problems. So we've looked at that a little bit, but we haven't done a lot in that direction. I'd be happy to talk
Last question.
Like, like in this finite volume formulation, the conservation is expressed as an integral relationship.
As an integral
Right.
conservation law, basically.
Is the order of the method connected to the order of the integral? The order of the quadrature?
So we're not really doing a quadrature in that sense. So although we think of initially starting with this integral of the cell average, we're looking at the Riemann problem as just being defined by the cell average on the two sides. So at least for these second order methods, the way that I've described it, we're not doing any quadrature. Now for the higher order, the sharp law methods, there is some quadrature involved in that, in approximating.
Well, you might have to do it at the boundary, right? So here you're using some kind of midpoint rule at the boundary. But for higher order, you would have to solve
You mean at
different
the boundaries
Riemann
of the grid
problems,
cell?
right? At one boundary.
Well, again, at the boundaries of the grid cell, we're not really looking at computing a flux. So we're not really integrating along the boundary. Instead, we're taking the state values on each side and using that to define the Riemann solution. And then we're taking the waves that come out of that, which are really based on piecewise constant data. And then the higher order accuracy comes from adding in these higher order terms in the Taylor series expansion that we can express as combinations of the waves and speeds again.
So you would also have to do that for the Vino scheme. Then you have more correction terms then.
So for the Wiener scheme, it's written differently. It's not done using that Lax-Wendorf framework. Instead, it's a semi-discrete method together with Runge-Kutta time stepping. So there you are calculating more approximations of what's going on at the interface at an instant in time, and then applying the Runge-Kutta time step.
So there you do.
But the way that what's being defined at the edge of the grid cell is, again, instead of being a flux, it's written in terms of these fluctuations that extends also to non-conservative problems. And it's based on looking at the waves that come out of the Riemann.
In your Rossby-Horowitz example, so if you put the Coriolis force into the Riemann solver, now there's a whole host of waves, right? We have Rossby waves, Kelvin waves, and you have gravity waves from before, and then there's just the geostrophic balance. So in your Riemann solve, do you try to tease all of those out separately, or are they somehow lumped together? Because there are separate eigenvalues, right, for each of those.
Yeah, I would have to look at the code. I think it was Christiane Helzel who was really working on that problem, and so I'm not sure exactly of the details of what went into the Riemann solver.
So maybe broader, just conceptually, how important it is it just most important to tease out the fastest couple waves, or what's the philosophy that goes into?
In terms of incorporating things into the Riemann solver from source terms, typically it's well, in the tsunami case, for example, it's the variation in the bottom bathymetry that balances the hydrostatic terms that you really have to build into the Riemann solver. If we have additional terms like Coriolis terms, in that case, we simply do that as a fractional step approach, Coriolis terms. And if we have bottom friction, which is also added, we do that as a fractional step. So we don't try to incorporate those into the Riemann solver. And so it's the terms that have to balance out with large terms in the divergence of flux that you need to.
And when you say fractional step, do you mean sort of it's pulled out separately? What?
Right. So I mean, we've solved the hyperbolic equation maybe with the bathymetry using these Riemann solver ideas, and then after advancing with that, then we take a time step on the remaining source terms. Just dq dt equals whatever source terms are left over, which in the case of say bottom friction would be just basically ODE in each grid cell.
So that might also be called like time splitting?
Yes.
Okay.
Okay, let's thank Randy again.
Thank you.